Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so it gives me great pleasure to introduce Omer Paneth, and he's going to tell us about our work with Yael Tauman Kalai on delegating RAM computations.
Okay, thanks, Daniel. Again, I'm Omer. I'm going to talk about delegating RAM computations. This is a joint work with Yael Kalai, and please feel free to stop me with questions anytime. Okay, so let's start with an example that will help us understand what is delegation and why do we need it. So let's say that someone gives you a pair of graphs, and your job is to decide whether these graphs are isomorphic or not. So in this example, the graphs are pretty small, so it might take you just a few seconds to realize that these graphs are really isomorphic. But what if the graphs are much bigger? So I'm going to leave this up so you can verify. It may take you a few seconds to verify. So just in case you haven't heard the exciting news, there's Baba has a brand new algorithm for deciding graph isomorphism that runs in quasi-polynomial time. So great, we can use Baba's algorithm. But since it's quasi-polynomial, when the graphs are pretty large, then running Baba's algorithm will still require a very, very long time. Now add to it the time that it takes you to read Baba's paper and implement the algorithm, then we're in very bad shape. So here is where outsourcing computation and delegation come to our rescue. So cloud computing platforms like Microsoft Azure, for example, they allow us to access computational resources that are far beyond what we have on our laptops. So what we can do now is take our two graphs, G and H, send them to Microsoft Azure. Azure will run the computation for us, and it will just give us the answer, which is in this case, no, the graphs are not isomorphic. So if you're a cryptographer, this is exactly the point where you start getting very suspicious. So don't get me wrong, we completely trust Microsoft. Microsoft has been nothing too good to us. There's a lot of cameras all around. But who knows, maybe we're not really talking to Azure, maybe we're talking to an imposter. Okay? And maybe for some reason they want us to get the wrong answer. Maybe they're just lazy, they want to save on computation. In any case, you know what they say, it's not paranoia if they really are out to get you. So now what we want to do is use crypto to do this securely. And the way this works is that together with a computation, we send some cryptographic challenge. And now using this challenge, the cloud can also compute a proof that it actually performed the computation correctly. So for us as clients, verifying this proof should be very easy, much, much easier than running the computation ourselves. And for the cloud, computing this proof should not incur too much overhead beyond the original computation, because remember that we are the ones that are actually paying for these CPU cycles. So just because we're following Ron's talk, let's just contrast it from the setting that Ron was mentioning. So here we're talking about the computational setting, where we use cryptography and we assume that even a cheating cloud runs in polynomial time. But we do insist on preserving this two-round communication complexity that we had in the insecure delegation. Okay. So this is what we call a delegation protocol. Researchers have been thinking about it for quite some time. And today we have this really amazing result of Kalai, Raz, and Rothblum that allows us to delegate any polynomial time computation based on the hardness of learning with errors. Good. Okay, so now we have this really fantastic tool. We can delegate massive computations securely. So this will definitely be useful. Maybe it will be useful for scientists. I'm sure you can come up with other examples. But we want to think big. We want to help as many people as possible. Maybe we want to get delegation into every computer. So we should really focus on computations that regular people do every day. So maybe we can think about email. So we all use email. Some of you will probably use it even before the end of this talk. And most of us have tons of emails in our inbox. So even a routine operation like searching for our emails can be pretty challenging. So maybe you can use delegation to help us securely outsource the task of searching for our emails. So the way this will work is something like this. First, you take your entire inbox, you upload it to the cloud together with the keyword. So this defines your computation. And then the cloud sends back the search result together with the proof. So you don't need to be an expert on delegation to realize that this solution is really all wrong, right? So first of all, by the time that it takes you to upload your entire inbox, you can already do the search yourself. Also, most of us, we store our inbox directly on the cloud. We don't save our emails locally. So if we don't trust the cloud, then how can we hope to verify the output of a computation where we don't even know what the computation is? So the problem here is that we're no longer thinking of very long computations over a short input. Now we want to delegate simple computations, but over a very large input or large memory. So the computations that we want to delegate are often of this form. You can think about searching through emails, delegating database queries, computing statistics over big data. And I think this type of computations is where the utility of delegation really comes from, even though graph isomorphism is also a very interesting problem. Okay. So if we want to deal with this type of computations, we need to do things a little bit different. So back to our email example. Mm-hmm. So you can think about the space, but yeah, from the picture it looks like the space is the issue, but the issue is really the input. Like, is the input short or long? Okay, but now it will be more clear. So we'll see what we actually want to do. So back to our email example, we can do something like this. Initially, when we first outsource our inbox to the cloud, we'll also compute a short hash or a digest of this inbox, and we're going to save it locally. Now, whenever we want to delegate to search for our inbox, we'll just send a keyword, and we'll get back the results together with the proof. And now we can verify this proof against the digest that we saved. Also, whenever we get a new email, we upload it to the cloud. Maybe it goes directly to the cloud. It doesn't matter. The cloud now sends us back an updated digest, this digest prime, that already includes the new email, and a proof that this new digest is really correct. And again, we can verify this proof against the old digest. So of course, these interactions can happen over and over again, and we want all the changes we make to our inbox to persist between interactions.
Can you just remind what CH is?
C is like a cryptographic challenge that you send together with the computation, and you just need it for the cloud needs it to compute the proof. We just
prime is as big as digest, or is it small, as big as the new email?
right. So ideally, what we want is that both digest, the new and the old, are always small. Specifically, we're going to repeat this with the new digest, so we don't want our parameters to slowly grow.
Are you thinking of digest prime as replacing digest, or?
Yeah. When I do this again, from now on, once I verify the proof, now digest prime is my new digest, and that's how I repeat. Good. So this is called a memory delegation protocol because we first outsource a large chunk of memory, and then we delegate computations over this memory. So this was defined by Chung et al. They gave a protocol for simple computations, and again, using the protocol of KRR, Kalai, Rosen, Rothblum, we can delegate any polynomial time computation. Okay, so memory delegation already comes much closer to what we need in this email example, but actually we're not quite there yet. So let me draw your attention to a major problem that we have with memory delegation that has to do with the efficiency of the cloud. So if we don't care about security, if we don't want the server to compute any proofs, it can actually search and update our inbox extremely fast, much faster than the size of the inbox. The way this works is that the cloud can compute an index over our emails that allows it to search and update in sublinear time. So think about something along the lines of binary search. But now we want security, we want to compute a proof. And even though our computation doesn't actually touch the entire inbox, in memory delegation, computing a proof is always proportional. The time to compute a proof is always proportional to the size of the entire memory. So really, computing a proof could be exponentially slower than running the computation. And this means that our protocol does result in tremendous overhead for the cloud. So let's stop and think about what's, yeah.
So why would it, you said it's proportional to the size of the memory, but not the size of the inbox? What do you mean by memory?
Memory is the input or, yeah, the size of the inbox. It's in memory. In this example, computing the proof will be proportional to the size of the entire inbox. So in this example, the memory is just the inbox.
And this is a claim about existing solutions, not about the concept. Right?
Yeah, it's a claim about both existing solutions and just the definition of memory delegation. So I'll go into the detail in a bit. So what's the problem here? I mean, originally I told you that in delegation protocols, the prover must be efficient, the cloud must be efficient, it has to have small overhead. Now I'm telling you that in memory delegation, the overhead of the cloud is actually huge. So there must have been some misunderstanding here. So the issue is that the efficiency of the cloud really depends on the model of computation that you're thinking about. So in memory delegation, we always model our computations, an existing memory delegation, the way it was defined and constructed, we always think about computations as Turing machines. And in the Turing machine model, any meaningful computation has to read through its input at least once. So we anyway pay for the size of the entire memory. But in real life, computations run not on Turing machines, they run on RAM. They don't run on RAMs, they run on computers. I wanted people to stay around, so thanks. They run on computers and they have random access to their memory. So if we really want to capture the efficiency of these type of sublinear computations that only touch a part of their memory, then we need to work with the more expressive models like random access machines or RAMs. So RAMs are definitely superior to Turing machines when we think about sublinear computations. But even when we think about computations that do touch their entire memory, then RAMs can still give us a quadratic speedup compared to Turing machines. Now remember that the computations that we want to delegate are already very large, so a quadratic speedup here could be very meaningful in practice. Okay, so what we're after is a delegation protocol for RAM computations. And before I tell you the result, let me define just a bit more precisely what is RAM delegation. So the definition has three parts: the syntax, the efficiency requirement, and the security or soundness. So the syntax of a RAM delegation protocol is as follows. We have a server and a client. At the first phase, the client wants to delegate a memory, capital D, and it also computes a digest of this memory. Now, in general, in this phase, we should also allow the server to do some one-time pre-processing of the memory before it stores it. This will be important for the server to later compute proofs and stuff like that. But just to simplify the notations on the slide, let's assume that the server saves the memory as is. In the second phase, the client wants to delegate a computation. So first of all, it samples a public challenge and a secret verification key. Then it sends the server the challenge together with the computation described as a RAM program M. Now it's the server's turn. The server is going to use a procedure that we call prove that basically executes the computation and computes a proof of correctness at the same time. So this procedure takes the challenge and the computation. It also has access to the memory. So here, if we want the server to be efficient, it's crucial that we also model the server as a RAM program. So the procedure proof has kind of random access into the memory. And what it outputs is the output of the computation, Z, D prime, which is the new digest of the computation after it was executed. So if the computation is read-only, if it doesn't modify the memory, D prime is just equal to D. And also a proof, P, for the correctness of Z and D prime. So the server sends this to the client, and using the verification key in the digest, the client verifies the proof. And if everything is OK, we accept the new digest, and we can repeat the second phase. Yeah. Yeah. Specifically, every time we repeat, we sample a new.
And is there a reason that it needs to be private inherently, or is it just that's what?
No, there's no reason. That's just what we're going to do today. I'm going to talk about this more when I state the result. Yeah.
Can you explain to us the difference between P, D, and D prime? D prime, I understand. That's the new digest. What's P and Z?
So Z is the output of the computation, what I claim the computation actually outputs. So I'm saying I'm running this computation. I got this result. The memory has this new digest in case you want to run another computation. So Z is what you actually care about. D is for the future. And P is just a proof that these are correct.
So Z is the result of the computation on the old D.
Yeah.
Capital D.
No, yeah.
And the P is the proof that that computation was performed correctly.
Right.
So for the Google example, it makes no sense. But in general computation, yeah.
Yeah.
Okay. Z.
So for the email example, it makes sense, right?
Yeah, so Z is like all the words you found that have the word bye-bye in there.
Yeah. Sure.
And the capital D can change. You can write to memory, right?
Yeah, you can write to memory. So in particular, D prime can be different than D.
There's no capital D prime in the slide.
Yeah, it's implicit, right? I mean, yeah.
So this model still doesn't capture the email example as it is now, as the emails are already on the server.
Right. I mean, you can think about the computation that writes the email. You can always, but the way it captures it is that
I can start it with an empty.
You can
mailbox.
start with
I
an
open
empty.
A mailbox now.
You have two options. Either you open your inbox empty, okay,
Yeah.
and then you can every time you get an email, you run this RAM computation. You run the second phase that just writes the email to the inbox, or you start with a full inbox, and then in that case, you have to compute a digest one time by yourself. These are kind of equivalent in terms of efficiency for you.
I don't have the inbox. They have it to begin with.
Had it to begin with.
Either you get them one by one, or you have them all to begin with. Yeah.
Related to the last two questions. So if I don't give you an a priori bound of the size of the memory, can you handle that?
Yeah.
So I can start off with like a tiny digest corresponding to a tiny memory. And
Right. Without loss of generality, you can always replace this first phase by an actual delegation round that initializes the memory, and you'll get the same efficiency for this. Okay. So this is syntax. More questions about syntax? Okay. So now the efficiency of the scheme. So when we think about the efficiency of delegation protocols, it's kind of useful to compare it to the insecure delegation where we don't compute any proofs. So ideally what we want is that the efficiency of every operation is exactly comparable, exactly the same as in the insecure case, up to some polynomial factor in the security parameter. So delegating the memory and computing the digest will be linear in the memory size time factor polynomial in the security parameter k. The running time of the server will also be proportional to the running time of the computation. And of course, running time is in the RAM model. Now what about verification? So in the insecure case, we don't really have verification. Here we require that the verification time is linear in the description size of the computation and the output. So we have to at least read those. And again, we pay a poly k factor on top of that. So this type of efficient verification implies that the length of the digest, the length of the proof and the verification key, they're all short. They're polynomial in the security parameter, and they're independent of the length of the computation.
The digest might be still large.
So the digest is small. The digest is just polynomial in k.
It's poly k?
Poly k.
Independent of the...
Independent of the computation.
No, the input.
Yes. It's just in our construction, it's just the output of a collision-resistant hash. Okay. So as you can see, this efficiency requirements are very tight. You can think about a more liberal requirement where if we delegate a time t computation, then the server runs in time polynomially related, t squared or t cubed. And so this is also a reasonable requirement. And in fact, in the protocol of KRR, the overhead of the server is quadratic. But today we will be able to improve this, and we'll get this tight notion of efficiency.
So you're saying that even for Turing machine, this is some improvement.
Right. Exactly. Okay. So we talked about syntax and efficiency. Now let's talk a bit about soundness and security. So we're going to consider a game between an adversary taking the role of the cloud and a challenger. At first, we let the adversary choose whatever computation and whatever memory it wants. Then the challenger computes the digest of this memory and also samples the challenge. And now the adversary chooses an output, a new digest, and a proof. And we say the adversary wins this game if the proof verifies, but the output or the new digest, either the output or the new digest are incorrect. So this is one way to define security. We can also consider a stronger notion of security where we let the adversary directly choose the digest. So now the digest doesn't have to be computed honestly. It may not even correspond to any actual memory. So if we want to talk about this stronger security, then we need to change the rest of the security game a bit. Now this game doesn't really make sense. So can someone tell me what's the problem with the game as it's written now? Right. So now D, capital D, is not defined. The real memory is not defined. So the correct computation is not defined. So what does it mean for the computation to be correct? So in this setting, we just require that the adversary can't prove that the same computation with the same digest lead to two different outcomes. and this is strictly strong. So this type of strong security with adversarially chosen digest is actually pretty useful. So think about settings where there's one party that delegates the memory, and then there are other parties that want to delegate computation over this memory. So even if you don't trust the first party that delegated the memory, even if they're colluding with the cloud, still you're getting a very meaningful notion of soundness. The cloud can't just prove any statement that it wants. And the strong security also have a bit more surprising applications in the theory of zero knowledge. If you're curious about that, then ask me in the end of the talk, and I'll say a bit more about that.
B doesn't reveal the size of the database as well, because you said it's the output of the collision resistance.
Right.
So can't even cheat in the size.
Yeah. Okay. So we do get this stronger security with adversarial digests. I'll say more about this in one slide, but for the rest of the talk, I'm mainly going to work with the simple definition, where the digest is computed honestly. Good. So this is the definition. Questions about that? Fantastic. So we can move on and talk about results. So our result is that we construct a delegation protocol for RAM computations, assuming sub-exponentially secure FHE, fully homomorphic encryption, or even simpler, a computational private information retrieval scheme. So this is just the same assumption used in the KRR protocol for Turing machines. So we get delegation for RAMs, essentially based on the same assumptions. I'll just mention that in our construction, we do use collision-resistant hash function, but this assumption already follows from FHE or peer.
So for languages and P, we need quasi-polynomials, so would that be simple?
So there's a small nuance here. So really what we need is a quasi-polynomial FHE, but sub-exponential collision-resistant hash function. So if you want to just not write collision-resistant hash function, this would be the assumption. Okay, so it's not completely the same, but it's very close. Okay, so let me mention some important properties of our construction. So first of all, as I mentioned, we get tight efficiency. The running time of the cloud is exactly proportional to the running time of the computation, not the running time of the computation squared, like in previous works. And again, running time is measured in the RAM model. So here we get another quadratic improvement over Turing machines. And of course, for sublinear computations, this improvement could be much, much more dramatic. We get security with adversarially chosen digests. There's a small caveat here. So in our construction, as I said, the digest is just a collision-resistant hash of the memory. And we don't want to let the adversary choose the hash function. We need to trust that it's collision-resistant. So in practice, it's not really a problem, because we do have trusted hash functions like SHA-2 or SHA-3. But in theory, what we do is we add the public parameters to our scheme that they just describe the hash function, and they're chosen honestly. Good. The next property I want to mention is adaptive soundness. So adaptive soundness means that we let the adversary choose its computation, not in the beginning, like in the previous slide, but also adaptively after seeing the challenge. So our construction is based on the KRR protocol, which is not adaptive. But let me just mention a new unpublished work of Justin, Yael, and Zvika, and they get an adaptive version of the KRR protocol and also of our scheme. And another wonderful thing they do is they improve the assumption from sub-exponential FHE to just standard polynomial FHE. So look forward to that.
Which means they remove collision resistance, like
If they want to get RAM, they also need to assume collision resistance. But again, it follows. And here, because we get rid of exponential assumptions, then it really follows. There is no caveat. Okay. So our protocol also have some limitations. So first of all, we only get a privately verifiable protocol. Not everybody can verify a proof, just someone that knows the secret verification key. Also, we don't get any secrecy. So Ron mentioned this property. It means that the memory and the computation, they're public. They're known to the cloud. So let me stress here an important distinction between our work and previous works. So usually, getting secrecy for delegation is not really a problem. You just run your delegation under fully homomorphic encryption. But in the context of RAM delegation, this transformation is not really applicable. So can someone tell me what's the problem? You can still run the update on the phone.
RAM, you can't do RAM.
Yeah. Why?
You need to touch everything.
Okay, exactly. This transformation loses all the efficiency of RAM delegation. Now the cloud will have to take the entire memory and use it under the FHE, so we completely lose the efficiency requirement that we want. Okay. So it seems like getting public verification and secrecy really requires very different techniques than what I'm going to show you today. And really there's a parallel line of works that achieve these properties based on program obfuscation. So I just want to do a short comparison between these results and obfuscation-based results. So lately there have been a lot of progress in obfuscating RAM programs. And this also gives you delegation for RAMs. And as I mentioned, these delegation protocols have public verification and secrecy. The drawback here is, well, first of all, the assumption, sub-exponential I/O instead of just LWE. And also, they need to assume that the digest is honestly computed. In fact, in these schemes, the digest is not even publicly computable. It contains secrets. So the cloud, can work with this digest, they can update the digest, but they can't just compute it from scratch. So when we think about this secret digest, this also makes the question of adaptive soundness a bit more complicated, because now we would like to let the adversary choose its computation adaptively, not only on the challenge, but also on the digest. That's even more important, because this is something that persists throughout the life of the system. So in our scheme, this is for free. The digest is publicly computable. Here they had to do some work. And the bottom line, what we know how to get today is adaptivity with respect to the digest, but we don't know how to get adaptivity with respect to the challenge. So this is just the state of...
So the digest needs to be generated honestly at the beginning, and thereafter I don't need to worry about it, or like every step in...
Just in the beginning.
Just in the beginning.
Yeah. Okay, so this is all I wanted to say about the result. Any questions so far? Yeah.
So what are the practical implications of assuming that the digest has to be honestly generated? I'm trying to get my head around that.
So one example that I gave is that maybe different parties, there's one party that delegates the memory, and then other parties want to actually compute on it. So this means that if the party that delegates the memory colludes with the cloud, there's a total break. The cloud can compute anything.
And just to check, you could also do this like in random oracle model, right? Like with snarks and stuff like that, right? That's if you just want verification.
Yeah, I'm going to get to that.
Oh, okay.
Yeah. Sorry, it's not like I'm just comparing to the obfuscation, but I'm going to explain how this relates to knowledge assumption and random oracles roughly halfway through the technical part. So wait for that. Okay. Good. Okay, so now we can...
Why are you comparing to obfuscation? Because that was the best thing that was known before it? No.
No, this is kind of a parallel line of works, and I think that it achieves these really interesting properties of public verification and secrecy.
Because of public verification.
Yeah, I just want to also, but still it's incomparable. So I just want to.
Stuff also achieves public.
Yeah, the random oracle stuff achieves everything. Everything is green.
No, not secrecy.
No, how do you get
No, we don't achieve secrecy. Right, you can't use secrecy. Okay, good point. But the random oracle achieves public verification, adaptive soundness, and the digest is public. And I don't know what you should write here, but okay. Good. So let's move on to talk about techniques. Yay. Okay. So maybe we want to construct a RAM delegation protocol, and a very natural place to start would be in memory delegation. So remember that RAM delegation is just memory delegation where the prover is much more efficient. So this is the first thing we tried. It really didn't work. We ended up doing something else. But I do want to tell you in just a couple of slides why this doesn't work. So if you lose me or if you want to take a little break, then the next two slides about memory delegation, they're kind of a tangent. So you can check your emails insecurely. Okay, so how do we construct memory delegation? So to see that, we need to go even further back to Turing machine delegation, simple Turing machine. So now the client delegates an input and a computation, and what it gets back is the output and a proof. And because the client knows the input and the computation, then it can verify this proof. So if we want to get memory delegation out of this, what we do is we look at specific constructions of delegation for Turing machines, and we look at how the verification procedure actually works. And what we see is that the verification doesn't actually need to read the entire input. It only needs Oracle access to a few locations of the low degree, of the input when it's encoded using an error correcting code called low degree extension. So if we want to get memory delegation, all we need to do is to have the server implement this Oracle for the client in a secure way. So the work of Chung et al. On memory delegation suggests two different methods of doing this. The first method is have the client compute a hash tree over the low degree extension. Now the digest is just the root of the hash tree. And the proof also contains an authentication path, which is basically a proof that the Oracle answer is consistent with the root. The second method is for the client to save one symbol of the low degree extension in a secret random location. So now using properties of low degree extension, the prover can actually prove consistency of any other location with the one location that the client knows. But if we want to keep the location secret, then we need to use FHE or secure function evaluation for this. Okay, so this is two ways to get memory delegation. Now we want to get RAM delegation. And we're going to start by just thinking about two very, very simple RAM computations. The one that just reads one bit from memory and the computation that just writes one bit. So if we're using the hash tree method, reading is actually pretty straightforward. But if we want to write even a single bit to the memory, then now all the locations of the low degree extension needs to change, and the cloud needs to recompute the entire hash tree, and obviously this is too slow. So if we were using the second method of saving one location in the low degree extension, we can actually write really fast. We can in fact update the digest without even communicating with the cloud. It's pretty amazing. But if we want to read even a single bit, then again, because we're using FHE, the cloud needs to take the entire memory and use it under the FHE. And again, this is too slow. Okay. So we didn't solve the problem, but at least we got this nice symmetric table out of this. So this is nice. No, so this is just like a toy example, right? So we just read one bit. It's not really clear how to extend it to any read-only computations. I mean, maybe you can, but we didn't.
So the problem is in both ways, the digest is a function of the low-degree extension.
That's a problem with memory delegation. Right? Yeah. This is kind of a problem with the approach, right? Yeah. So we're going to really do something else. Okay, so we're done talking about things that don't work. Let's talk about what does work. It will be a good time for everybody to tune back in if you weren't listening. So now I'm going to give you a one-slide summary of our approach. This slide doesn't really mean anything, but it's really easy to remember, and you can use it to convince other people that you attended the talk, so pay attention. So any RAM computation, we can think about it as having two components. The actual computation running on the CPU and the external memory. So we know how to delegate computation. This is the KRR protocol. We also know how to delegate memory. I'll remind you how to do that in the next slide. Now all we need to do is to make these two solutions play well together. Okay? Doesn't mean anything, right?
Yeah. What do you mean? We just saw that in the memo way, it's not a great solution so far.
Yeah, okay. This is just like to help you remember what's going on.
Us not listening.
I'm going to combine so our high-level approach is to combine known solutions for delegating memory and for delegating computation. I'll explain exactly what delegating memory means in the next slide. So let's review this really classic scheme of Goldreich-Ostrovsky.
You do want me to remember something about the memory.
Yeah.
But what went wrong with it again?
What went wrong with memory delegation?
Yeah, in terms of solving what you want to do right now. Previous slide.
So in memory delegation, the magic of getting rid of the input, of delegating the input to someone else and still having all the delegation protocol works, is that you can't really get rid of the input. You need to remember something about it, but not directly on the input, but the low degree extension of the input. And
that you're still going to use somehow.
I'm not going to use it.
Okay, so you're going to use old methods. Fine.
Exactly.
Because we're not going to use low-degree extension, because low-degree extension has the property that you change one, you need to work so hard to change everything else.
Okay.
I'm going to use really old stuff.
So does it mean that in particular you will give us a different approach for memory delegation also?
Yeah, that's a good.
Yeah. Well, this approach will contain KRR inside, but so if you just want the shortest path from KRR to memory delegation, you should use the old approach. But this gives you a new approach, a completely different protocol.
So do I need to remember low degree extension or no?
No, this will use KRR mostly as a black box. You don't need to know the low degree extension anymore, if this is your goal. But I recommend it's pretty nice. Okay. Good. So let's start by reviewing this really classic scheme of Goldreich-Ostrovsky for outsourcing memory. So what's the setting here? So here we have a trusted CPU that is interacting with untrusted memory. So everything we read and write can be modified adversarially. And now we want to add authentication to this so that the CPU can trust that it's really that the memory is really acting consistently. Okay. So we all know that we can do this based on collision-resistant hash function. This idea of hash trees. Now, originally Goldreich-Ostrovsky also wanted to achieve secrecy, so they developed this mechanism of oblivious RAMs. Here we don't care about secrecy. We just care about the authenticity of the memory. So let me re-describe this hash tree solution in a way that is a bit more abstract. So now the CPU will save a short digest of the memory. This is just the root of the hash tree. Whenever we read something, we can also obtain a short proof of correctness. This is just an authentication path in the tree. And also whenever we write something, we can obtain an updated digest for the memory, and again, a short proof that this digest is correct. So now using this terminology, we can take any RAM computation and describe it using this long table, and we call this the transcript of the computation. So what do we have here? So the computation proceeds from top to bottom, not from left to right. In every row, we have the state of the CPU, the memory operation, which is either read or write, the memory address for this operation, the bit that is read or written, the new digest after the operation, and of course, a proof of consistency. So if we're reading something, the proof authenticates the bit with respect to the digest. If we're writing something, the proof authenticates the new digest with respect to the old digest from the previous line. Okay, so we say that such a transcript is valid if for every pair of adjacent row in this table, everything kind of checks out. So for example, here we would check that starting from state S5, if we read the bit B5, we will really transition into S6. And in state S6, we write B6 to the first address of memory. And also P6 is a good proof authenticating D4 with respect to D3. So this is a long to say, but it's very intuitive, right? Good. So again, the intuition is that the transcript is valid. This means that either this computation described here is really consistent. Every time we write something, when we later read the same location, we get the same thing. Or one of the proofs in this transcript has to be bogus. And this means that we can actually take this transcript and use it to find a collision in the hash function. Okay, so why am I troubling you with these annoying transcript and all this complicated bookkeeping? So we're going to use this notion of transcript to reduce the task of designing a RAM delegation scheme to designing a different type of proof system. So in a RAM delegation scheme, we're trying to prove a statement of this form. A RAM machine M given access to memory D, output Z. But alternatively, I can also prove an equivalent statement that says that given a hash function, I know how to find a valid transcript for this computation. So assuming collision-resistant hash function, these two statements are really equivalent. But still, they're very different statements. If you want to prove these statements, you need to use different type of delegation protocols. So concretely, the statement above is deterministic, while the statement below is non-deterministic. It has a witness, which is just the transcript. Also, to prove the statement above, you just need a sound argument. But below, you really need an argument of knowledge, because this statement is computational. Even if the statement above is false, still there exists a valid transcript, but the cheating prover may not be able to find this transcript efficiently. So far, it seems like we're much better off working with the statement above. But here's the punch. The statement above is about RAM computations, and the statement below is just about Turing machines. So even if this computation above has a huge memory, verifying the transcript can be done in small space. Now, of course, we can take any RAM computation and simulate it on a Turing machine, but this will blow up the running time. The point here is that verifying a transcript, the time to verify a transcript is exactly proportional to the RAM running time of the computation.
Because it just goes down.
Yeah, because just you need to verify the number of lines, which is just the number of steps in the RAM computation. Good. So it seems like we might have made some progress. Now we just need to construct an argument of knowledge for non-deterministic Turing machines that has the same efficiency properties that we mentioned before. The problem is that this turns out to be kind of a notoriously difficult task. So what do I mean by that? So today we only know how to construct these things either in the random oracle model or based on strong non-falsifiable knowledge assumptions. So this is already good to know. If you are willing to work in the random oracle model and make knowledge assumptions, then you already have RAM delegation. This is what Daniel mentioned before. So I don't think there's actually, I don't think that this theorem is ever explicitly stated anywhere. But interestingly, in practical works of delegation, they do sometimes follow this approach. I think that this is simply because RAM computations are much more efficient. But today we really want to get something in the standard model based on standard assumptions like LWE. And here we have some bad news. So there's this lower bound of Gentry and Wicks that tells us that you can't construct such a thing based on falsifiable assumptions using a black box reduction. So today, crossing this Gentry-Wicks barrier is considered to be a very difficult task. And really, we're not going to cross it today. We're just going to go around it. So the point is that we don't really need delegation for any non-deterministic Turing machine. We just care about one very specific computation that verifies a transcript. And this computation has this very nice structure that we can exploit. Specifically, we say that this is a computation with a locally verifiable witness. So roughly what I mean by that is that you can take your witness, break it into small pieces, and now you can verify these pieces one by one, and every piece can be verified without a lot of work. So if you're thinking about verifying a transcript, every piece is just 2 adjacent rows. Yeah?
Sorry, maybe I'm not following. So why is that lower bound relevant when yours is interactive? It's non-interactive.
No, so we're looking for a non-interactive solution. Yeah, we're just 2 messages. Okay, so for this type of non-deterministic statements, this lower bound no longer applies, and really we do get a protocol based on LWE. So our protocol is just basically the same protocol as KRR, but with a different analysis. So we definitely need to open up the analysis of KRR. So here is one page of their proof. Specifically, you can see it's page 103. It's pretty technical stuff. Now, the other 102 pages are also very technical. So the point here is that working with changing the proof of KRR can be maybe unpleasant. Luckily for us, we don't really need to do it. We don't even need to talk about low-degree extensions. We can work with an abstraction of the KRR proof. Here we kind of use the main part of the proof as a black box, and we just build on top of that. So this abstraction of the KRR proof is pretty useful. It was already used in several other works. I think it's something that is really worth knowing, so let me tell you a bit more about this abstraction. So if you look at the heart of the KRR proof, what it gives you in very clean terms is something called arguments of local satisfiability for non-deterministic Turing machines. So this will be the main object that we're going to work with from now. I'm going to define exactly what this means in the next slide. For now, just think about it as arguments that have some weak notion of soundness. So from arguments of local satisfiability, KRR go all the way to full-fledged arguments for deterministic Turing machines. So first they did it with bounded space, and later they removed that. And today we're going to use arguments of local satisfiability to get what we need, arguments of knowledge for non-deterministic Turing machines with locally verifiable witnesses. Okay? And again, using collision-resistant hash functions and this notion of transcripts, we can get arguments for deterministic RAMs. So I think Neil mentioned this before. We also get an alternative construction of arguments for Turing machines that have better efficiency than the arguments of KRR. Good. So this type of modular view of our construction allows us to dramatically simplify the proof, but it also allows us to get stronger results. So everything, yeah. Well, just this. So it also allows us to get stronger results. So if we improve these arguments in the bottom, these improvements kind of propagate up. Concretely, in a work with Guy Rothblum, we get arguments of local satisfiability that are publicly verifiable based on graded encodings. And this new work that I mentioned of Justin, Yael, and Zvika, they get adaptive arguments and based on just polynomial time assumptions. So now by doing virtually no extra work, we can get full-fledged arguments for Turing machines and RAM that have all these nice properties. Good. So this is the power of abstraction. Yeah.
And the second arrow only needs collision resistance.
Yeah. Oh, here you use FHE, and here you use nothing, and here you use collision resistance. Okay, and here you also use nothing. So in that sense, these two arrows, they don't subsume this arrow, because I mean you can actually interpret all of these results in the MIP settings, where this would be unconditional, and this more efficient proof will still be assuming collision-resistant hash functions. Wait.
Wait. So collision-resistant hash functions were only in the purple.
Yeah, everything purple. Yeah.
Oh, everything.
Okay, great. So today we're going to talk about this arrow, and I'll start by defining what are arguments of local satisfiability for non-deterministic Turing machines. Are we doing on time? When did we start? 35. Okay, so as you probably know, we can describe any non-deterministic computation as a tableau, but again, it goes from bottom to top now. And this tableau is just a big table of Boolean variables, Vi. And now the computation is described by a Boolean formula, phi, that takes all these Vi variables, and it basically checks that in the bottom row, we're consistent with the correct input. In the top row, we're really describing an accepting state. And everywhere in the middle, all the local constraints of the computation are satisfied. So if the formula phi is satisfiable, if it has a satisfying assignment, then it means that this happens if and only if this non-deterministic computation is accepting. So this is just standard stuff. So now I'm going to define what it means for the formula phi to be locally satisfiable. And this is just a relaxation of full-fledged satisfiability. So we say that phi is locally satisfiable with a locality parameter kappa if there exists an algorithm that we call a k-local assignment generator that basically samples partial assignments for this tableau. So the way this works is that you first need to specify a set of at most kappa variables from your tableau, and then you think of this algorithm as this big red button that you can press, and you get an assignment for the variables in your set. The problem is that this button is probabilistic. Every time you press it, you may get something completely different. So basically, the assignment generator defines for every set of at most kappa variables a distribution over assignments. So for this to be a good, a valid local assignment generator, the assignments that it samples, they need to satisfy a couple of properties. The first property is called everywhere consistency. And it just means that for every set of variables and for every assignment that you sample for them, this assignment should be consistent with the computation. So it should satisfy every clause in phi that is over the variables in your set.
So V1 to Vn is everything.
Everything. Right. But we're using the fact that this phi is kind of local. Every clause is just working on maybe 3 variables. So if these 3 variables are in your set, this clause better be satisfied. Okay. Intuitively, if you look at this assignment, it will look like something that is actually consistent with the computation. The second property is called no signaling. It's a bit trickier. So let's spend some time here. So the no signaling property tells you what's supposed to happen when you sample 2 assignments for 2 sets of variables that have an intersection. Specifically tells you what is supposed to happen in this intersection. So I'm going to tell you exactly what's supposed to happen, but before we do that, let's try and kind of guess what we can require here. So one thing we can require is that these 2 assignments always agree on the intersection. So this turns out to be very strong. It basically implies that the local assignment generator is kind of deterministic. It always agrees with one global assignment. So now there's really no difference between local satisfiability and global satisfiability. Too strong for us. So let's try something else. These 2 assignments, they don't have to agree. Maybe we put no requirement. Okay? These 2 assignments, they're not required to be consistent in any way. So this turns out to be too weak. So if kappa is pretty small, I'll tell you what it is later, then any set of kappa variables will be kind of trivially satisfiable. Intuitively, we don't capture these, the global structure of the computation that connects the input to the output like this. Okay, so let's try one more time. This time it's going to be just right. So the no signaling property says that the two assignments, they don't have to be the same on the intersection, but they have to have the same distribution. So for example, if I sample an assignment for the first set, and one of these gray variables here always gets the value 0 with probability 1. So this means that when I sample an assignment for the second set, then the same variable should also get the value 0 with probability 1. This is kind of what we're going to use out of this property. No, no joint distribution. Just sample an assignment for these and restrict it to the gray area. Sample an assignment for this and restrict it. These two distributions are identical. The marginal distribution, yeah.
They actually need to be identical.
They can be. We do work with a definition where they're statistically close, and there's a new work now that I mentioned that actually work with computational indistinguishability.
No signaling soundness?
No, so here there's no MIP, there's nothing. This is just like a tableau and something that reads out of this tableau. There's no PCPs or anything like this. Just you read out of the tableau, and what you read has these very natural statistical properties of, when you read something that intersects, you need to require something. So this is like maybe the only thing that I can come up with that you should require that actually helps us. Okay, good. So this is the no signaling property. Questions about that? So we're going to think about kappa as being polynomial in the security parameter, and we say that a formula phi, if it is locally satisfiable, if there exists a kappa local assignment generator that satisfies these two properties. So I defined the main thing. Okay, so back to our outline. We have arguments of local satisfiability. This is what we get out of the KRR proof. So this is kind of a clean thing that you can know about the KRR proof. It gives you this, no low degree extension. And again, we're going to use it to get arguments of knowledge for non-deterministic Turing machines. Actually, just to keep things simple today, we're going to, again, focus on the one computation that we care about, the computation that verifies a transcript. So this is what we're going to see today. And in fact, I was cheating a little bit. This is also what we do in the paper. We never actually define this more general notion. The reason I tell you about it is because I think it gives the right intuition. All we're going to use in the proof is the fact that this transcript is locally verifiable. Okay? So if you want, you can define this thing and make the proof go through, I'm sure. Okay. Great. So now I think we're ready to describe the protocol. So we want to prove a statement of this form. Yeah.
You're saying that one way to prove a KRR that's what they do. So
well, they don't go here, but they go somewhere. That's what they do.
The previous slide, the thing
Yeah.
with the tableau.
Yeah. Well,
Previous.
the wrong direction.
This. Right.
Yeah. So KRR you can think about the proof as consisting of two parts, this part and this part.
And no signaling in the context of two provers. You could think about a tableau and about these.
Right. So if you actually read their paper, they don't do that. Okay, this is the intuition of what they do. They don't actually define this notion, achieve this notion, and use it as a black box. They actually kind of modify the construction of this to get this directly. But you could do this. In the work with Guy, we actually do this formally, and you can also get it from this work on ramps. But this was their intuition all along. This is how they describe their approach. Okay, so this is the right direction. Okay. So this is what we're going to do today, and let's describe the protocol. So we want to prove a statement of this form. A RAM program outputs M outputs Z, given access to memory with digest D. Okay? So the way we're going to prove this is we're going to use the KRR protocol to prove that there exists a local assignment generator for this specific computation that verifies a transcript, and it has this very nice structure. So in this computation, the witness is just the transcript, and we read the witness line by line, and between every line we have this block that verifies consistency of the two lines. And also the first block, verification block, also explicitly verifies that the digest is the correct digest that we care about. And the last verification block explicitly checks that the last output is equal to z.
Can you just quickly remind what those
things are? So this is the state, the memory operation. It's not so important, but the state, the memory operation, the index, the bit that you read, and the digest. Okay? You don't really need to remember that. Good. So now we want to prove soundness. We want to prove that if the statement above is false, then give me any local assignment generator for this computation. I can use this local assignment generator to break the security of a hash function. So let's do that. So the proof goes like this. The first thing we need to do is take our RAM computation and execute it in our head and obtain the real transcript of this computation. Now what happens when we try to verify this real transcript? So every intermediate verification block is going to succeed because this transcript was computed correctly. But the last verification block is going to fail because the statement is false. The computation doesn't really output z. So we call this computation on the left the correct computation. And also every partial assignment to this tableau, we say that it's correct if it agrees with the correct computation. So now someone gives us a local assignment generator, and it's adversarial. It may not sample assignments that are correct, but what we're going to prove is that either all the assignments that we sample here are correct, or we can use this to find collisions in a hash. So how do we do that? So we first look at the assignment to the first verification block. So now using the everywhere consistency property, we know that that this verification succeeds. And in particular, this means that the assignment to the first row of the transcript has to be correct. We explicitly check that the digest is the correct one. So also we know that the second line of the transcript verifies against the first one. And since the first one is correct, if the second line is incorrect, that means that we found a false proof and we find the hash collision. Assuming that this doesn't happen, then the second line of the transcript here has to be correct as well. Okay, so now we move on and sample an assignment for the second verification block. And now because the second row of the transcript is in the intersection of the first and the second blocks, we can use the no signaling property to argue that if it was correct before, then it's also correct now. So now we're going to use the everywhere consistency again to argue that the third line of the transcript has to be correct or we break a collision-resistant hash. And we keep alternating between the everywhere consistency property and the no signaling property until we get that the final row of the transcript needs to be correct. And this means that the final verification block has to fail. Okay? But remember that everywhere consistency means that this has to be consistent with the formula phi. It has to describe an accepting computation. So this is where the contradiction comes from. Okay, so this is all I wanted to say about the proof. I think there's, if you know the KRR proof, it's basically.
I know I'm wrong, but where am I wrong? No signaling is strong, right? You cannot. These distributions have to be indistinguishable from each other.
Right.
But all you seem to be saying right here is that it is a consistent.
Right. I'm using a very specific. Corollary of no signaling that says that if if an assignment is equal to a specific value in one assignment, then it will be equal also in the other.
Right. More than that, apparently.
No, I don't think I need more than that.
So that's a much weaker non-signaling requirement. No?
You have some reverse implications, right? You think that no signaling is necessary for this kind of stuff to work, right? I mean, I don't know.
You should be using it for correctness, right? Not.
No. I'm using it for soundness. This is the soundness proof, right? I mean.
Okay, for soundness, but you need it to be.
But I need like a very specific thing. I need that if you sample an assignment for one variable and it's equal to 1 with probability 1, then it will also be equal to 1 if I sample something else.
Can I ask a related question? The marginal distribution is a point distribution. Sorry.
Yeah, I understand that. So why do you need such a strong notion of no signaling?
The thing that is using the local assignment generator, that is going to use the full-blown no signaling property.
Right. True. True.
But not for the argument that you just made.
Yeah, that's a good point. Right. And you really do use the full power of no signaling. You don't just use it for predicates that compare. Okay, good.
So I'm missing a higher order bit. So who sends a transcript? That's already linear. That's already very long, right? So you never send a transcript.
No. So this real correct transcript is something that only exists in the proof.
In the proof as well.
Yeah, the verifier never computes this. But when you try to when we try to prove soundness, this is what we usually do. We take like the prover, even though it sends short proofs, we kind of try to recover from it a huge transcript. So this is what we do in the
efficient prover though. Are you running the KRR protocol T times, or are you running a KRR protocol on a...
Fantastic. So the KRR protocol, I said that the efficiency, it's a great question. The efficiency of the KRR protocol, I said that it's quadratic. You can actually say something more refined. It's proportional to the time times the space of the computation. So if you're thinking about computation, in general, computations, the space can be as large as the time. If you're thinking about low space computations, you actually do get something that is tight. And one of the benefits of proving something about the transcript is that you're always working with small space. Basically, you're outsourcing the space using this collision-resistant hash function. Yeah.
So you're saying that for this type of computation with the sort of local checks, the local assignment generator actually implies that there is a complete assignment, like to the full thing, right?
You can use it to recover.
How is that different? Maybe from my intuition, like why does that not hold for just complete any non-deterministic computation, like where does that go wrong? Because we know.
Where does that go wrong? Great. So we kind of use induction. We started from this being correct, right? So even if you think about non-deterministic computation that only has one witness and kind of, the only way to write this whole thing non-deterministically is this one particular way. The problem is that when we look at things locally, we don't know that. It could be when we read the first thing, every time we read, we could get something completely different.
Even at the very first row,
right.
The bottom row, there's no notion of correct. Really.
Right, right. So all we need is this notion of local correctness, which is exactly what this more general type of NP computations is. Good. So more questions about the proof. Okay. So we're basically done. I just want to mention some interesting future directions about delegation. So the first future direction is to get a delegation scheme that is both adaptive and publicly verifiable. This is something that we currently don't know how to do without knowledge assumptions, or not even based on obfuscation. And I think this type of proof systems are really cool because they allow us to reuse the challenge. So in particular, this means that someone trusted can sample and challenge once and for all and publish it as a CRS. And now everybody can use the CRS to prove anything they want to everyone else. So this is maybe the closest we'll get to NP-style proofs in the succinct deterministic settings. Okay. The second future direction I want to mention is kind of an obvious one.
But when you write it that way,
yeah.
Then this challenge doesn't have to be small.
It should be. It doesn't have to be small, but you should at least don't read the entire challenge in order to verify. Maybe you want to read a few bits of it. Right. Yeah, that would also be a very useful.
Yeah. So just not exactly on this. At the beginning, you said you could get this whole thing from here. Where is it coming from?
It's hidden in the local satisfiability. So this thing on the bottom here that says arguments for local satisfiability, it's hidden in the KR proof. That's the assumption that we inherit. Okay. Great. So the second direction is really an obvious direction. Implement a delegation protocol that is efficient enough to be used in practice. So I think that so far in the field of delegation, there was this really productive cooperation between theory and practice. So every time we get this improvement in our theory, then this also inspires a lot of implementation projects. And I'll take Alessandro for helping me out with references here. So one thing that we can learn by looking at these examples is that thinking about RAM computations, tight efficiency, getting rid of quadratic overheads, can be really crucial for getting a practical protocol. So all of these results, they're in different settings than ours. Some of them use interaction, many rounds of interaction. Some of them have large pre-processing, so they only get amortized efficiency. Some of these are based on knowledge assumptions. So it will be great to get a practical protocol that doesn't rely on any of these. So now we know how to do it in theory, and the time for implementations is right. Okay, that's all I wanted to say. Thanks.